Good morning, afternoon, evening, ladies and gentlemen, everyone who's watching this presentation online. I am delighted to welcome you to today's presentation unveiling the beauty of Newton-Raphson fractals. My name is Enrique Lugo Martinez, and I am a student from the first semester of the Masters in Nanotechnology in Tecnológico de Monterrey, Campus Monterrey. Today I'll present you my final project of computer simulations, which is an exploration into the enchanting world of computational art, mathematics, and the Newton-Raphson method. This class was taught by Professor Mario Villada Balbuena. Today we'll journey through the significance of finding roots of polynomials, unravel the Newton-Raphson method, and then delve into the captivating world of Newton-Raphson fractals. Obviously, this is going to be done by visualizing the roots of a complex function. This is not only these are not only pretty pictures; they carry deep insights of the behavior of complex functions and offer us a glimpse into the infinite wonders of mathematics. I will also show you the MATLAB program, how I implemented the Newton-Raphson method, and how to visualize the roots of a complex function, or better said, the behavior of how to find the roots of a complex function. And finally, and not least, my conclusions. So polynomials are fundamental mathematical constructs. Um, they carry, I mean, they have a wide-ranging applications, whether it's calculating interest rates in finance, simulating physical systems in physics, or optimizing engineering designs. So polynomial equations underpin many real-world problems. So identifying their roots provides crucial insights and solutions. So, for example, I have here in my slide fifth-order polynomial f of x, which I also plotted it here in this figure. What I also did is to put some markers on this polynomial's root. Basically, a root of a polynomial is when the function or the polynomial is equal to zero. I mean, the point where the polynomial is uh, equal to zero. Exactly. So for this function, these are its roots. I also want to tell that polynomials can be simple or incredibly complex with multiple roots, like I'm showing you here, some of which are not easily expressed analytically. This complexity makes it infeasible to rely solely on pencil and paper methods for finding roots, which means analytically solving them. So numerical methods such as the Newton-Raphson method are essential for tackling these challenging polynomial equations. And yes, this is what will lead us to the fractals. The essence of this method lies on its iterative approach. It starts with an initial guess, x sub 0, for a root, which obviously may not be accurate. The method then iteratively refines this guess to approach a more precise root. And given this initial guess as x sub 0, the method computes the function's value at this point, denoted as f of x sub 0, and then the derivate's value at this point, denoted as f prime of x sub 0, then calculates the next approximation x sub 1, which is equal to x sub 0 minus the quotient uh, of the evaluated function and its derivative also evaluated in that point, in that initial guess. Here I have a graphical figure of how to visualize how this method works. So basically this process is repeated iteratively with each new x value getting closer to the actual root. So a general form of the Newton-Raphson method is written with the n sub indexes, which is also shown here, just to implement it easier, or make it easier to be implemented as a program. Let's go to the next slide. Where things get especially interesting is if we ask about finding roots in the complex plane. In this case, it's not that easy to visualize the method by itself by using a tangent line to the function that we're trying to find the root, but nevertheless, the same logic can be followed, where a linear approximation around the initial guess will equal 0, and then we can use that that linear approximation, and follow the Newton-Raphson method. So, for example, let's try to find the roots of a third-order complex polynomial, which I'm showing you here. And I also did my homework of showing you the roots of this polynomial, this complex function, by using a plot of a unit circle, and also the roots of this polynomial are presented here with these red markers or red dots. So let's continue. If we apply the Newton-Raphson method to this function at each point in the complex plane, the number of iterations required for the Newton-Raphson method to converge to a root is then used to color a point, or the point. And each of these points generates an attractive image that's known as a fractal. More specifically, because we're using the Newton-Raphson method, they are known as Newton-Raphson fractals. The point where we found the root is colored depending on which solution is found and how long it took to arrive at the solution. So, for example, I'm showing you here two images, two figures, 1 and 2. In figure 1, I'm revealing the regions where roots are found quickly, or better said, how is the convergence behavior. For example, rapid convergence in specific areas correspond to darker or blue contour lines, indicating well-behaved roots, which are found in this place. To illustrate this even further, it is just not the convergence rate that is sensitive to initial conditions, but also the root, what the root actually converged to. So in figure 2, the figure 2 colors the regions where points converge to one of the three roots shaded as green, yellow, and blue. So the points are in these these regions, and all these points are converging to this specific root, and also the same for every each endpoint in this plot. So if we go to the next slide, I will explain the implementation of the MATLAB programs. This provided code is a function that implements the Newton-Raphson method by finding the root of a function. This numerical method is used to find the values of z that makes f sub z equal to 0 in this case. The function just takes three input arguments: the function, its derivative, and the initial guess. This function returns z, which is the estimated root, and con, which just counts the number of iterations required to converge to the root. It is basically a while loop that continues until the absolute difference between z and w is less than the error tolerance, which I also put it there, which is 10 to the minus 7 power. Secondly, I use this fractal function, which aims to generate fractal patterns using the Newton-Raphson method. So it takes as input the complex function, again, its derivative, an initial point, set sub-zero, and here's what's important is to define a grid width, which is W, and the resolution, which is n. So this creates a grid of complex numbers and applies the Newton-Raphson method to each grid point and visualizes the result. And last but not least, I show you the set of inputs that I use to generate the shown fractals. So we are arriving to the end of my presentation, and I just wanted to tell that polynomial root finding powered by the Newton-Raphson method is a cornerstone of modern problem solving. It allows us to tackle complex equations, as we see, not um, yes, I mean complex in both its meanings, which hard could mean hard equations or difficult equations, but also complex functions from the complex theory, and understand the mathematical roots of real-world issues. For example, what we found here is the Newton-Raphson fractal for the function f of z set to the third power minus 1, and this was done by using the Newton-Raphson method to find its roots. And also the convergence behavior and the regions where points converge to one of the three roots were plotted and found to form a Newton-Raphson fractal, which I'm showing you one of the pictures here uh, that I created by using my fractal function. So just wanted to end my presentation here. If you have any questions, please leave them in the comments below. I also want to thank you for the attention for this video, and see you in the next one.